Yeah, so good afternoon, everyone, and welcome to today's section on classification techniques in machine learning. So, from previous class, we had a section where we talked about introduction to machine learning, and we devised the concept of regression. We also talked about error analysis in machine learning, where we also talked about regression. Also, we also talked about the different arms, or how will I say, the different classifications of machine learning, where we talked about supervised learning. Does get an overview of them, which is supervised learning, semi-supervised. We had reinforcement learning and unsupervised learning. So last section, which was on Monday, we talked about on only regression analysis, which is on supervised learning. So today we'll be talking about classification techniques and machine learning, which is a subset of unsupervised learning, and we'll also touch a bit on supervised learning, unsupervised learning, and semi-supervised learning for today's lecture. So from last class also, we talked about just get a simple understanding of mathematics for machine learning. What are the prerequisites, or what are the needed knowledge for someone to have if the person will pursue a career in machine learning, in fact of having an academic background. So it's not only coding, it is beyond coding if you want to like dedicate more of your time to it. So we also talked about a little concept for those who are mathematically inclined or who would love to pursue a field in it and understand how their model works. So we talked about the little mathematics that works in them. We talked about that matrix calculation, and vector calculus. So those are some application of mathematics. We also talked about the techniques, that statistical techniques we used, and machine learning techniques. So we found out that there's a difference of when we are having a statistical techniques and we have machine learning techniques. So initially, machine learning was derived from the concepts of statistical techniques. But as time goes on, they begin to devise different techniques or different algorithmic techniques that work, which is beyond the scope of statistics. So we saw that, which was also in last class. So if you are not in the last class we had, so the videos, the slides, and the notebook I also used in the whole program would also be shared alongside after, I guess it should be after the end of the section or after the end of the bootcamp, whichever way it is, everything will be shared to you. So thank you once again for joining on this call. Yeah. So for me, we'll move further. So these are the outline for today's section. So we're talking about the basic concept. We'll be talking about classification examples, illustrative diagrams. We'll talk about semi-supervised learning, unsupervised learning, classification algorithms, and evaluation metrics. I think from last class also, we talked about the evaluation metrics in regression. Well, we found a concept that regression analysis, which is a continuous and variable, for evaluating it, it is always evaluated using error metrics. And we found there are different error metrics, but we limited ourselves to only three, which is the mean absolute error, the mean squared error, and the root mean squared error. So there was we'll be saying different evaluation metric in classification analysis. Now from this, I guess we can see something on this screen here. So we can see something like this, which is one, this is showing the spam. This is showing a spam. Why this one that is white is showing no spam? Why there's another one showing which is a spam? So this is like a classifier algorithm. Like let's say we're taking logistic regression. So this is a logistic regression in which these are data sets, or we established the fact, also talk about different kind of data sets also in our last class. So we can just assume this is a tabular data set in which either it is spam or it's not a spam. It is the target variable, or which are dependent variable. Then we fit this data set into our classifier, which is a logistic regression classifier. So we have a logistic regression classifier. So the classifier does its algorithm computation and gives us and classify them into two different into two different segments, which is either it's an inbox or it's a spam mail. So this is what we're talking about today, classification. So it does classify them into two discrete classes. So it is either as an inbox or it's a spam folder. So those are things we'll be talking about today in today's section. So now we'll be talking about these are just the basic concept of what classification is. So like I established in the previous one, classification is a method of predicting similar information from a value of categorical target or categorical class variable. So now in classification has to do with a discrete class. When we say discrete class, it means they are classes that we can quantify, or they are classes in which they are known. So it is not like a continuous variable where it can be of any number or any value. So in terms of classification, when we are classifying, just like we have in our previous one, when we said either it's a spam or it's not a spam. So if it's not a spam, it can be in your inbox. And if you come down to the fact of using a Gmail, let's assume in a Gmail, you get on your Gmail is grouped into, your inbox itself is grouped into different segments. You have like your update folder, you have your promotion folder, you have your social folder, and you now have the inbox. Now, if we want to have a mail, that is another case of where we're doing a classification metric. Let's say, for example, you are trying to get a mail. Gmail already has like a classification algorithm that obviously scan through your mail and see if the mail that is being sent, if it is from a recognized email address. So making it, if it's not from a recognized email address, it's Gmail will know that, oh, this might be a spam mail. It drops it in your spam folder. But if it is not a spam mail, then it's Gmail try and scan it and try, okay, which of this folder can this mail be grouped into? Is it a social? Is it a social, your social folder, which is like a notification from your Facebook, or is it like an update from, let me say, for example, you just subscribe to probably a social media or a company, let's say for example Jumia, or let's say your bank mail comes in and your update. So those are ways in which it can classify messages. So we can see that beyond in classification, we are not just limited to classifying only two different classes where we have only either it occur yes or no, or either it's a spam or it's not a spam. We also have a multi-class classification. I also have a multi-label classification. Yeah, and for those of us joining, please, if you have any question along the line, I will be monitoring the chat room. Please also just fix your message there. If there's anything not clear, also I would quickly pop in and answer your question. So I want everyone to follow at once. Now, in the area of classification, also that I just finished explaining, we also have image classification. So the term image classification, so we all know image means we are dealing with an image. So, and if we're dealing with an image, there are algorithms or there are algorithms or there are techniques in which you use in dealing with an image classification. But today we'll be talking about tabular classification, in which we are talking about tabular data sets. So we just have rows and columns. So also in yesterday class, we talked about on Monday class rather, we talked about where we had a column which was categorical, which was alphabetical, but we were unable to use that column. So today, in today's class, the code lecture we'll be having, you would see a place where I had to do like an encoding to see how we can convert and from alphabetical column to a numerical column. Now, so the next thing is, what are the supervised learning, the concept of supervised learning? So the first thing we have your data. So your data can be in labeled instance. So when they say labeled instance, it means they are grouped into different features. So features can also be talked about as what are the attributes? They are also same thing like attribute. What are the attributes of a person? A particular human being. He has nose, he has eyes. Those are like attributes of a person. So your data also have an attribute. So your attributes are called the x-axis, then your target variable is called the y-axis. Now, for example, they said email either it's marked as a spam or it's not a spam. That is your target variable, what you are trying to predict. Now, in trying to solve a problem using machine learning, we have different sets in which I explained. We said we have a training set, then we have a holdout set, and we also have a test set. Now, I think in the last class, I didn't make mention of holdout set. So it is still the same thing. So if you're having a training set is what you are training your model on. A holdout set is what you are testing your model on. Why the test set itself is what your model will be predicting in the future. Let's say, for example, we build a system, a system that determines if or the particular amount of loan a person can access based on one, we can use the person's geographical area, and based on the person past data, or based on the person past way in which behavior in which the person has borrowed money before, based on the person current account balance, based on the person salary that enters per month. So we can know, oh, this is how we can borrow the person. Now, let's say, for example, we want to build that kind of system that gives out loan. Now, what we first do is we first take a training set. A training set is our past data set. Now, from that training set, we can try to split it into two. So which is the training and the holdout. So what we are trying to do is that the holdout is what we use to evaluate our model if it is doing well based on an evaluation metric that we'll be discussing soon. So now the test set is the future that we'll be predicting into. So let's say, for example, we deploy that model. If a customer comes in and inputs his data, that test set is what the customer is imputing. So a new customer is coming into the system and imputing his data based on his past record. And because we've trained our model already, based on our training set and our holdout set, it tries to learn the feature based on the training and the holdout set and produces a target, which is the amount the person can borrow based on the test result, or which is the test set or the test data in which the person passed into the system. So it gives out, okay, this is the range of money what we can give out to you. So this is an example of when you're having your training set, your holdout set, and your test set. So in case of you are trying to participate in a competition or an hackathon per se, your test set is what the competitor organizer would be training your model on, would be evaluating your model on. So they will give you a training set and a test set. Then you have to split your training set, your training data into a training set and an holdout set. I think I did that also in the last class where we attributed, okay, this will be our test size. So that is for data. Now, feature, like I said, they are attribute value pairs which are characterized by X. So your amount of feature can be of any number, but note your target variable, which your dependent variable, can only be one column. For the case of supervised learning, it can only be one column, but your independent variable can be any number of attributes. They can be up to a million, they can be up to 1,000, depending on the amount of available data that is given to you. Now we have an experimentation cycle. So in experimentation cycle, so like ML is an experimental field in the sense that we try to model our algorithm to best suit our data. So there is no just one algorithm that is the king of all data. They are, in case of natural language processing, I think naive Bayes over time has proved to be the best ML algorithm that work for natural language processing. While in case of tabular data, gradient boosting machines have been the best. So it does not mean that other algorithms are not good. No, you have to experiment with those algorithms that we'll be discussing also to see which of them perfectly fits your data set. Then you begin to work on the parameters. So we'll also talk about hyperparameter tuning. So that's like the experimental circle of machine learning. Now for evaluation are the metrics evaluation are the metrics in which you use to prove if your machine learning model is doing well, if your algorithm is doing well. For the case of regression, we have the mean absolute error, we have the standard and the root mean squared error, and we have the mean squared error. So for the case of classification, we will be checking also, we'll be seeing our accuracy, we'll be seeing F1 score, we'll be seeing your confusion matrix. So we'll be seeing precision and sensitivity. So these are different evaluation metrics, so we'll also be seeing. Now, in classification, we have the term called overfitting and underfitting. So overfitting and underfitting, this comes when you are, once time, your underfitting comes when your training data, when there is like an high bias towards your training data and it is not learning your test data. Let's say, for example, your model is underfitting, your model is not learning well from your data set. It is just predicting based on few information it got. So, once you are producing a result, your result will be biased towards a particular subset because your model did not generalize or try to learn the whole data set. While in the case of overfitting, your model went inside your data, understand your data, and get like a good understanding. But when it is trying to predict it is not predicting well. So in the case of underfitting, we have an high bias. While in the case of overfitting, we have a case of low bias. Then we also have like what are like different examples in classification. So like I said, in classification, it means you're learning a discrete function, which is what classification. So now our classification can fall on different scale. If it is binary, binary means you're predicting two different classes. So if it's more than two classes, it becomes a multi-class classification. Now, if it's also, there's another interesting field, which is called multi-label classification. In the area of multi-label classification, it means among your classes, a particular class can belong to different labels. Let's say, for example, we want to predict different transportation system. Now, in the transportation industry, there are different ways you can transport. Now, you can transport by road, or let me use, you can transport by a vehicle, that's by a car. You can transport by a bike. You can transport by a bus. You can also transport by air. You can transport by ship. Now, in the area of we want to find, okay, let's say, for example, we are transporting by vehicle. In also transporting by vehicle, we have different model vehicle. Now, let's say we are giving a data set that comprises of different vehicles. What we're doing is that if we are saying, okay, what label would our car fall into? Your car will fall into a vehicle, or let's say we have two different models, which is let me use Innocent Moto. We have Innocent has a car. I think what's the name again? I think Caris. They have a car named Caris. That's a model car named Caris. Then they also have another one. I think Land Cruiser also. Yes. So those two, they are made by Innocent. They are different cars, right? They are different car models. So, but if we want to classify them, we'll classify them under vehicle. But they can fall under different classes, meaning they can fall under, that means those cars are under two different classes. The one that Caris is like a saloon car, while the other Land Cruiser is it's not a saloon car, it's another kind of car, like a pickup, like a pickup. But they all fall under the classes or the label of they are all vehicles, and they can be used to transport by road. So in multi-label, it means a particular instance can be classified on different classes. So that's what multi-label does. While in the case of multi-class, it means you have different classes in which a particular instance can fall only under one class. So there's a difference between a multi-class and multi-label. So in multi-label, one particular instance can fall under two different classes, while in multi-class, an instance can fall only on an instance. So that's the difference between a multi-class and a multi-label. While in binary, you're predicting two different occurrences. Either it happens or it does not happen. So either it's a girl or it's a boy. So that's an example. Now, different examples of classification. So we have in medical diagnosis. So it is used in medical imaging. We have automatic essay graders. So we also use it. This field is called natural language processing. It tries to like find out like the relationship among your essay based on like the past inputs that has been given. It's based on the past input of data it has been trained on. Then it trains your first, it try and check if there are grammatical errors. If there are no grammatical errors, it try and there are different there are different metrics in which is passed into it for you to grade your essay. So this is a field, automatic essay grader is called natural language processing. Other field under natural language processing is also text to speech. Yeah, text to speech can be also be seen as a field under natural language processing. Chatbot is also a field under natural language processing. Then language, changing language, that's language translation also, natural language processing. So in the case of fraud detection, so in fraud detection, there are only two things that can happen. Is either a fraud happen or it does not. So that's another case in which you can have it. And we can also have it on a recommender system. It does in recommending system, we have if a particular person will buy this, or a particular person will buy this, a particular person will buy this. So it just depends. If, for example, a particular person would love to buy a shoe. Now there are different shoe sizes. We have Nike, we have different Balenciaga, we have just name them, Adidas also, yeah. So those are like three, they are different classes or different shoe sizes. So we would have to like, okay, which of them is the person likely to buy based on the person's past results? So that's like a recommendation engine using like a multi-class classification system. So we also have DNA and protein sequencing. I think this is a field also in the area of deep learning. And this was done by DeepMind, yeah, DeepMind, the one that developed a machine learning system that defeated the world's best Go player. Yeah, so they also developed alpha sequencing in the area of protein sequencing. So in the next one, we'll be having, so this is a simple classification diagram. So just for us to get an idea before we start writing the code. And so we can see that from the total of our table, we have a table of, so we have two different tables. I hope everyone can see what I'm drawing on the screen. Please, someone should also indicate on the chat if you can see what I'm drawing on the screen. I want to know if it is visible. So I drew a line over the training set and test set. Please, if you can see. Yeah, okay, thank you very much. Yeah, thank you. Yeah, so we can see that there are two different instances. We see we have the training set and we see we have the test set. Now, in this case, if you notice, we have 10 training. So you can see it here, 10. So we have 10. And we also have, we also have 5. So this is an example where we have a training set and a test set. So like in our case, this can be like a holdout set, right? This can be a holdout set. Now, these are different attributes. We have attribute 1, attribute 2, and attribute 3. So this attribute 1, it has its meaning. Attribute 2 also has its meaning. Attribute 3 has its meaning. Now, if you notice from here, we have two different classes. What are the classes? We have either it's a no or it's a yes. And our occurrences for no is 1, 2, 3, 4, 5, 6, 7. So we are having 7 no's and 7 no's and 3 yes. So in this case, we are having an imbalanced data. So when we say something is imbalanced, it means the ratio or the probability between both of them are not the same thing. So it means the probability. So in this case, we're having a ratio of 70% to 30%. So this is like an imbalanced data. But we also talk about how to undo imbalanced data also along the way. Now, these are classes. You see, we have a class of either a no or a yes. Now, what this does, the first thing is that we pass in our model. We pass in our model, which is induction. It learns what your model. This is the learning algorithm. So this can be any of our classification algorithm we'll be using. If it's like a KNN, if it's a logistic regression or a decision tree. So it learns it. This is the learning algorithm that is being passed into it. This is the data set. The data set is passed into the learning algorithm. Now, so it learns the model. It learns the model, it finds the relationship here, and produces what? A training model here. So our algorithm, this is our algorithm, and this is our data set, right? So both of them are passed into, that means the data set is passed into the algorithm, which forms the learn model. Now the learn model now produces a model, which is in our case, if in our last class where we had something now fits. So this is like a case in which you are fitting your data set into your algorithm. So this is what the induction does. Now, in the case of where we want to make the prediction, after you fit in, your model already understands what your data set attribute is, and it learns it. That is the case of this model here. It learns it already. Now, we can now apply our test data set into the model. So the process of applying your test data set into the model is what we have what your deduction. So you are trying to deduce what would be the class based on these three attributes and based on the model in which you've learned already. So this is just how it works, right? So this is just how everything works in our case. So we are trying to, from our training data set, we pass it into our learning algorithm, which is the learn model. then our learn model fits it into it and get a relationship. Then you pass in your test data set into your model, which is then we try to get a deduction on our classes. So in our case now, we can try to evaluate, okay, what will be the result? What will be the result? It can be that no, or a particular class can be that yes. We don't know yet. It's until we try to make like a prediction, that's when we can get a result based on our test data. I guess this can now give us an overview of how the whole process of machine learning classification is being done. Now let's quickly move to the next slide. So if there's any question, please also let me know. Now, there is something I fixed here. So we have baseline classifiers. So machine learning is not the answer to every problem. So before you can try to apply machine learning, there are steps in which we also made mention in our last class. We said that there's a process of data collection, there's a process of data analysis, there's a process of data pre-processing, there's a process of data visualization. Then before we come into what machine learning, there are problems that require that simple heuristic approaches that they can be solved. So not all problems can be solved with machine learning. But if you identify a problem that can be solved with machine learning, then you can solve it with machine learning. So the first thing is try to ask yourself a logical question on how can I solve this problem with machine learning before you dive into using machine learning. So it's not as if you are trying to cut a stick. You're trying to cut a stick, not a big log of wood or just a simple a plain wood. You're trying to cut a plain wood with an axe when you can use a simple saw to file it. So obviously to cut it, but it might even damage your plain wood the more by not giving it the desired shape. So it's best to first plan your approach to see if machine learning can solve the problem. So if it can, fine, then you now define what are the machine learning approach I can take in solving it. So what is the problem, or which kind of classification or which kind of learning will my problem fit that I want to solve? Is it a supervised learning? Is it an unsupervised learning? Is it semi-supervised, or it's an unsupervised learning problem? Now, another thing is assess whether or not machine learning has a benefit. So in solving the problem, you also try to make an analysis of if we are solving this problem with machine learning and it has to do with computational expensivity, if what we are trying to do, would it be of benefit? So those are things you can try to check or put in checklist before you start approaching the problem. But it's also nice to also like try and go out and search for questions on how to go about this. Now, let's quickly brush down to semi-supervised learning. Now, in the case of semi-supervised, we can see in our other data set where I said we have an imbalanced data set of 70 to, so this is it. We have a 70 to 30%. So let's say, for example, in our unsupervised learning problem, you always have almost the case set, you almost have a labeled data set of 10% to an unlabeled data set to 90%, right? So in the case of semi-supervised, as it implies, I said in the last class, it is both supervised and unsupervised. So with the part in which it is labeled is called the supervised, while the part which is unlabeled is called the unsupervised. Like I said, in unsupervised, we don't have a label class, we don't have a target class. So in this case, you have like a small proportion of a data set that has been labeled. Then you have to fit in an algorithm to try and learn also from the unlabeled data set. Is anyone speaking? Okay. So you are trying to learn from both the labeled data set and both the unlabeled data set. So it means you are performing both a supervised learning problem together and an unsupervised learning problem together. So just note the difference is that in a semi-supervised, your labeled data set is very small and you have a very large chunk of unlabeled data set. So where your algorithm would be learning from both the labeled and the unlabeled data set to give you the result. In all cases of machine learning, you must always get a result. So that's just it. In the case, if it is a supervised, unsupervised, a reinforcement learning or a deep learning problem, you must always get a result because you are trying to predict something based on the data that you already have or that is being fed to the algorithm. Now, we also have unsupervised learning. Now, I would want to dwell a bit more on this. Now, in the case of unsupervised learning, like I said, supervised learning, there is a labeled data, while in unsupervised, we don't have a labeled data or a target data. Now, in unsupervised learning, your machine learning algorithm would be to analyze or find a cluster in the unlabeled data set, in the sense that your algorithm would try to find a relationship in your test data. Now, let's quickly dive a bit down to supervised learning. Let me go back to this classification diagram. Now, if we notice, there is this class in which it is labeled in red. This, for this part, should be what we are predicting, right? But if we want to convert this old data to an unsupervised learning, what we'll do is we would not fit in this guy, this class. So we only fit in our attribute, which is attribute 1, attribute 2. Oh, sorry. We'll be fitting in attribute 1, attribute 2, and attribute 3. So those are the only 3 attributes we'll be fitting in. Then it would have to learn by itself. The algorithm will fit in it. It will have to learn by itself. Okay, what is the relationship among these guys? So it can try to do either a clustering or try and find an association between those 3 attributes and produces us a result. So that's just the difference. So in supervised, we pass in a class, while in unsupervised, we do not pass in any class. So let me go back to my slide. Now, in this case, this is the input data. So if you notice, let me check if I can zoom in. Okay. Yeah. So this, in this case now, you can see this is a case of you're having your raw data, right? So if we're having a raw data, if you notice, we have different shapes, different, so they are all clustered together. They are all like in this array, everything are together. Now, what we do is we pass in what we want to do is now we want to try and classify or cluster them into different places. So we have different colors. We have red, we have green, then we have I think purple. Yeah, purple. So this is the interpretation. So the interpretation is we're passing this our data into an algorithm. So we'll also be seeing what are the different unsupervised learning algorithm we'll be using. So they are different. So those algorithms are different, totally different from supervised learning. So we'll be seeing them also. So those unsupervised learning algorithms, try and find the relationship. What are the features that are important? What makes some features similar to another? So it try and find the relationship and produces a result. So this is our output. So the process is passing in your input data, you try and find the interpretation, then you pass it into an algorithm. The algorithm itself that does the whole pre-processing, not you. Your own is to gather the data and pass it into an algorithm. Then the algorithm does the pre-processing and produces for you an output. So if you look at the output and you see that this output is not something I desire, or this is not what I would prefer, or this is not what I would want, you can try and retrain the whole process again. Like I said, it's an experimental circle. So you try and experiment the whole process to think and see, okay, if you have gotten an optimal values, or if you have gotten a result that is suitable with you, or you have gotten, in the case of unsupervised, different clusters or different associations that are suitable for you. So before you can now say, okay, you have already trained your model, then you pick in, this is the model I've trained, and this is my result output. Then you can continue your process on testing on new data sets. Now, so these are applications. Okay, so let me quickly answer Mr. Oladipu's question. So he said, who write an algorithm to use on the data? So throughout the phase of the learning we'll be having in this bootcamp, we'll be using a library called scikit-learn. So I would, when it's time for me to code, I'll quickly brush through and we'll see. So scikit-learn it's an open source library. I think someone also mentioned it along the line of this bootcamp. It's an open source library in which you can develop, you can go and contribute. So you can go and contribute and see, okay, how it was written. If you yourself, you can also write an algorithm to use for your process. So it is not that it's not an uncoded principle or a one-way path that you must use an algorithm. You can write your algorithm yourself to use. You can try and tune your algorithm to use if you know the steps that it follows. For example, logistic regression, what it uses, it finds trace, find, get a probability, then you apply the sigmoid function to convert it into two different outputs, either it occur or it does not occur. So in the sigmoid function, anything that falls below 0 becomes 0. Anything that falls after 0 becomes 1. So that's like an example. You can write your algorithm yourself, but what is the essence of reinventing the wheel when it has already been done by someone already? Now you can, that's the beauty of open source. You can go online and use another person's code that has already been written. So in our case, we call it libraries. So it has already been written. So why it is open source, you can go and contribute. If you try and see that you are making a modification and you feel, yes, others can benefit from this modification I do, you can also go online and submit the code you've written. So the code base. So if the people that maintains the code base, that's the people that maintain scikit-learn code base, consider, oh, this would be a good addition. They can also add it also. Or you can decide to open source it and make it a library on its own, where people can also download and also use. So you can either write your own algorithm yourself, or you use other people's algorithm that was been written. And another beauty of this is that you can also go online and read papers that explain most of these algorithms and try and implement what was written in the papers. So there are different ways you can go about it. There's no a simple hardware way. But for the course of this bootcamp, we'll be using scikit-learn. And I'll also touch a bit on another library that was written by a list of researchers from Yandex. That's a company from Russia. So I hope that answers your question, Mr. Ladipupo. So in continuation of that, so there are different applications in which we use unsupervised learning. So we have the process of, we can use it in news section. You want to classify a news. You want to try and say, okay, which of these segments will the particular news falls into? Will it fall into the football section? Will it fall into the breaking news section? Will it fall into local news or world news? So based on the content of the news, they try and find the relationship there and gives you a result. Another example is in computer vision. Another one is in medical imaging. Then we have recommendation engine and customer segmentation. So customer segmentation is you are segmenting your customers into different outputs. So, or how they spend, or what they spend on, or what are the things they would likely buy. So that's like a customer segmentation problem. So if you are working on a problem, you first have to define what you want to solve with the problem, because a particular data set can be used to solve different problems based on what you want it to solve for you. So don't see that, okay, there's only, if you have a data set, there's only one problem you can solve. No, if your data set can solve more than one problem. So it does depend on what you define for it to solve for you. That's what you would have to train your algorithm to solve for. Now, in unsupervised, like I said, there are two fields in unsupervised. We have clustering. So in clustering, you are trying to discover there's a grouping in between them, or there is a relationship in between them. So in the example that was made here, they said you are grouping customer, for example. So you are grouping customer by purchasing behavior, right? So this is a case of clustering. You are trying to cluster them based on how they buy, based on their purchasing behavior, or based on their purchasing power. Another one is association. So in the case of association, you are trying to check, okay, if a person buys this, or based on how people buy this, buy X, they will also tend to buy Y. So if they tend to buy Y, it means whenever a person comes to buy X, so let's say whenever a person comes to buy a phone, they are always likely to buy a pouch for the phone or a screen guard to guide the phone. So hence, if a person comes and buy a phone, the next thing you should show the person is that, oh, this pouch will also be useful for your phone. Come and buy this pouch. So those are the two areas of unsupervised. We have both the clustering and we have association. So in clustering, you are grouping them. While in association, you are trying to find the relationship between, if a person does this, the person would likely do this. That's like an association. Now, there are algorithms we use. So there are different algorithms we use in the area of unsupervised learning. So we have dimensionality reduction. It means you are trying to reduce your dimension or your number of attributes into a seizable number. Like say, for example, we need a simple target column. We can try and find the relationship within them and reduce it to a single column, which will be our target variable. Or in case of clustering, we have what? A K-means clustering. So in K-means clustering, what it does, K-means is the most common algorithm for unsupervised. What it does is try to find a cluster. Like I said, it works in what? In numerical. But from the question Mr. Oladipupo asked, he asked about an algorithm. Now, there is this new algorithm that was written by, I think, a group of people. I saw it sometime by K-mode. So, like what K-means does for numerical. So, whichever value that is being passed to must be numerical. Why in the case of numerical, it means it will be in number 1, 2, and 3. Why in the case of K-mode, the data that is being passed into are categorical, means they are alphabetical data. They don't need what to be encoded, right? So if you pass in if you have like a list of data, in the case of in the case of where we have the news section, we want to say, okay, which of this category will this news fall into? Now, what KMO does is that it collects your data, that's the whole content of the data, you pass it into the algorithm, and you try to find, okay, this is the section in which your algorithm is fitting. So in the area of K-means, it uses numerical data. While in the area of K-mode, it uses categorical data. While also we also have hierarchical clustering. It also works similar to K-means clustering, but there are different procedures, or there are different ways in which the algorithm try to find a relationship. Now, okay, so there are different classification algorithms. So some are very, very common to us. We know them. One is logistic regression. So logistic regression work based on the principle of linear regression using the least square method. But in the case of logistic regression, where linear regression tries to find a discrete or make it continuous, logistic regression converts it to a discrete values, applying a sigmoid function. I think a sigmoid function is a mathematical method. So I would also show it to us also along the line. That's when we start coding. I would quickly show us a snippet also, so we can see what a sigmoid function does. So what it does is that it tries to penalize all results after zero, before zero rather to zero, then any result after 0 to 1. So that's if, for example, we're classifying in a case, if it is to rain or it is not to rain. In the case of k nearest neighbor, it also tries to find like an hyperplane between between our attributes. Then we also have support vector machines. These are old statistical techniques. Then we have the decision tree. So this one should be decision tree. Yeah, decision tree. So decision tree works based on finding the information gain, or try to find creating different tree and leaf node of a feature, and try to find and aggregate or example them based on which of them occurs the most. So in undergradient boosting machine, it also work based on decision tree. But the difference is that in gradient boosting machine, most gradient boosting machine use different ensembling techniques. So it can be that you are stacking them, it is combining all the leaf nodes together to form one simple predictor, or that in case of averaging, it means it's taking everything into occurrence and averaging them, or it is trying to take all of them and find the most occurring. So it can either work both based on the mean or based on the mode. So also, like I said, I would also show us an algorithm written by a group of researchers from Yandex, CatBoost also. So those are different gradient boosting machines, and they are used for classification. So we're not just limited to only these. There are a lot of algorithms that you can fall back to and use. So if you pick one algorithm, try and optimize it to get the best relationship for your data. So in the case of optimizing an algorithm, it is called hyperparameter tuning. Now, how can we evaluate a classification method? Now, in evaluating a classification method, there are different principles, or there are different evaluation metrics so we use. Now we can try to find the accuracy. Like in our case now, where we had, if it occurs from this classification diagram, we have two different classes of either no or yes, right? Now let's say, for example, we had, for this our test set, what normally we should have should be 2 no. This is just an example, and 3 yes, right? But let's say what our algorithm not performed, because we have 5 different attributes here, 5 different occurrences, or 5 different data points. So what our class should be 2 no and 3 yes. But in our case, what we did, or what we got were 4 no and 1 yes. So we can try and find, okay, the accuracy of this, we can try and find it. What will be the accuracy? The accuracy will be, since we are to get 4 node from here, 4 no rather, and we got 1 yes. But instead, we are to get 3 yes and 2 no. So let's assume all things be equal, meaning all the attributes, each of the attributes were correct. Now, what was not correct here? 2 were not correct here. It means 2 of our no should have been yes, but our algorithm did not classify it well. Then from our yes, we were having 3, we're having lesser than what? 3. So we're having 2. So now, from this now, we are having only 3 positive values that are correct. We should have 2 no's and we had 1 yes, which is 3. So 3 of 5 would be, we are having a percentage of an accuracy of 60%, right? We're having an accuracy of what? 60%. Please, I hope most of my diagrams are actually, or the little things I'm writing, I'm currently writing my trackpad, so it's quite hard. So we are having something about 60%, right? So this is a simple accuracy method that will classify ourselves, and we can say, oh, this is our model in which you trained is not particularly doing well. Now, let us say, for example, when I said, oh, we want this to do extremely well. Let me try and erase here. So let me erase this. Yeah. So let's say, for example, we want this to do well. We now retrain our model again by doing different hyperparameter or optimization on our model. Then we find out that, okay, we increase it to 3 no, then 2 yes. 3 no, then 2 yes. Now, in this case, we are still having our no should be 2, but we are getting 3. So it means 1 is wrong. So, but we are having 2 no, we should be having 3. It means also we are missing 1. So the correct values here will be what? 2 nodes and 2 yes, which is what? 4. Then our total occurrence is 5, right? So if we divide 4 by 5, we should be having an accuracy of what? 80%. So this is a simple analysis of how accuracy is being calculated. So let's quickly move back to our class. Yeah, predictive accuracy. So what this one does is what? The number of correct classification, then the total number of what? Of test cases. So your test cases means the total number of occurrence, which is n. The total number of data points. In our case there, it was 5. So we see that we have 2 different cases where we have an accuracy of 60% and an accuracy of what? 80%. So you can also try and look for a way in which you can optimize it to get what? 100%. But most times, if you are dealing with an imbalanced data set or an imbalanced data set where you are having a very, very low occurrence, accuracy might not be the best method to solve it. So we also see there are different evaluation metrics that we can also use for those ones. Now, we have what? Efficiency. So efficiency is the time it takes to construct your model. So there are some models that takes time to construct. They take a lot of time to construct. So you also check if your model is robust to handling noise and missing values. So like we said in some of our class, we said there are some ways in which you can handle missing values. In handling missing values, you can either leave it or you allow what. When I say leave it, it means you want your model to be able to handle it. Why there are some algorithms that cannot handle missing values. So what they do is that you must fill it, that you must impute something into it. So you have those are how you can evaluate, okay, what kind of machine learning algorithms you want to use. If it's a robust algorithm and if it is scalable and if it is interpretable. So you have to check, okay, if your model can be interpreted. So most times they call decision tree and gradient boosting methods in the academic field. Most times they call them a black box model because you cannot interpret them. But they call linear regression and logistic regression. a glass box. A glass box means you can see through it. It means you can interpret what the model is predicting. That's from a standpoint from the academics, you can interpret it. Now, but in the case of those decision tree, there's a new method that you can use to interpret it. I think they call it sharply additive values. It works on the principle of games theory. So you can also explore that. I would also make mention of it in our case. But what decision tree model does that? It can show you what are the best performing feature. What are like based on what the algorithm learns. It can show you, okay, among these attributes I had, these were the attributes that worked best for me. So it can do those ones for you. Those are like a case of what interpretability. Then we also have compactness of your model. How compact is your model? So when they say compact is your model, how deep? In the case of decision tree, how many numbers of trees you are building? So you also see something that we call estimators. We see what they call a learning rate. So in the terms of estimators, it means how many numbers of trees are you building? So if you are building 1,000 numbers of trees, it means your model will be estimating for a particular occurrence. It will be estimating 100 different trees. So there'll be like let's say we're using 1,000 estimators. It means your model will have to find 1,000 method, try and find like 1,000 method in which it can solve that problem, then estimate everything to give you a single response. So that's an example of how deep your tree is. So now, as I said, accuracy is one measure. So it is not only the only method. We'll also see like, okay, there are other methods in which what we can use. So now look at this. They said in classification involving, that's let me quickly. So in classification involving skewed or highly imbalanced data, that's e.g. in financial fraud detection, where we are interested only in the minority class. So in the case of in financial institution, fraud barely happens. So when they say something barely happens, it means in the case of it happens like 1% of over 99% in transaction. So that's the case of a perfectly imbalanced data or an highly imbalanced data. So in that case, you can never use accuracy as an evaluation metric, because let's say, for example, we have 100 occurrence and only one it's a fraud. If our model wants to predict, our model can be very, very biased. We can say, okay, everything itself, it's a fraud. So if the accuracy that will be coming up, since we are only having one occurrence, which our model is wrongly classifying, it can give us an accuracy of 99%. And you might say, oh, my model is doing perfectly well. 99% is almost 100%. Let me quickly deploy this and take it to the business people for them to say that, oh, we already have a fraud detection system. But you see that in all cases, it will never detect one single fraud. Why? Because we are using the wrong evaluation of metric. So another standpoint is defining a good evaluation metric matters a lot in your field of doing machine learning. So accuracy is not the only method. So we will see other methods in which we use also. Now, let's say, for example, let's say the class of interest is commonly called the positive class and the negative class. So in our case, when they say negative, it means a class that is not to occur. Let's take, for example, if a fraud is to occur, it can be the positive class. If a fraud would not occur, it can be the negative class. So when they say a negative class, it means it is the opposite, right? It is the opposite of it occurring. So we have two different classes: the positive class in occurring and the negative class for it not to occur. Please, if there's any question, please also drop it. So now let's quickly dive into confusion metrics. So like I said, there are different evaluation metrics we use in the area of machine learning. So in confusion matrix, confusion matrix is a performance measurement for machine learning classification problems where the output can be two or more classes. It's a table, like the name implies, it's a matrix, a square matrix. So if you are having, let's say for example, we are having 7 occurrences, that's 7 classes, which is a multi-class problem. It means our confusion matrix will be having a 7 by 7 matrix. So it's always a square matrix. So we'll be having this TP represents a true positive. So right, So TP means a true positive. So let me explain. A true positive means, let's say, I will come down to use this case of being pregnant. Let me zoom in so we can see. So now let's look at this. So this is where we have a true negative. Now in the area of true negative, it says you are not what? Pregnant. So what we want to do is that we want to classify if a particular person is pregnant or not. So we bring in two different boys, or we bring in a man and a woman rather. But because of the man is having a protruded stomach, and the woman is also having a protruded stomach, and we said, oh, our machine learning algorithm should learn, okay, which of them is pregnant. From a neutral standpoint, a normal human being will know that a man can't be pregnant, right? In all cases, a woman should be pregnant. Now, but if our machine learning algorithm is to now learn and see that, okay, based on relationship. Now, if it's saying a man is not pregnant, that is a true negative, because a man cannot be pregnant. Like I said, we have the positive class, we have the negative class. So the negative class is a class that did not occur. Now, in true negative, it means the particular person is not pregnant. Well, so once you see true, which is TN, it means it is perfectly classified. Then another one we have false positive. So when they say false positive, it means our machine learning algorithm is saying, oh, you are pregnant, a man is pregnant, which is not the case. So when they say false positive, it means our algorithm is doing the wrong thing, calling it the right thing. So it is classifying a wrong values into a correct class. So that's in the case of false positive, where you are saying a man is pregnant. So if we go down to false negative, a false negative means a woman that is pregnant, but our algorithm is saying that, oh, woman, you are not pregnant, you just have a big stomach. So that is what a false negative means. So false negative means our algorithm is classifying an occurrence that is actually true into a class that is it is the opposite of it, which is false. Now, while in the area of true positive, it is classifying, saying that, oh, you're a woman, oh, perfectly you're pregnant. It means our algorithm is classifying a correct class into its actual class. Now, so we can see from here, we have the cases of true positive and false positive, then we have false negative, and we have true negative. So in knowing if our machine do well, or if our algorithm do well, what we try to look at is the true positive and the true negative. So those are the two that shows us that, oh, our model is doing perfectly well. A true positive and the true negative. It means it is accurately classifying them into their respective class. While the ones that are not doing well are the false positive and the false negative. So false positive is that we're getting the wrong prediction from the other classes, while false negative, it means we are getting the wrong prediction from from the right classes, right? So this is an example. So now all or most evaluation metric you use in classification, in machine learning under classification, build up on confusion matrix. So it works based on a true positive and true negative. Now, in evaluating the machine learning, I outlined 5 different methods. Now, precision. So when they say something is precise, it means we want to get the accurate answer. That is a simple thing of what they call precision. So precision, we need the precise answer. So now, in the case of precision, I'll just be giving us, okay, what are the use case of precision, where it is used. Now, precision is useful in the case where false positive is a high concern. So when we say false positive, we know that false positive means the opposite class of what we don't want. Example, in the case of fraud detection, where we say if it's a fraud, it's positive, and if it's not a fraud, it is is negative. So in the case, we don't want to classify what is not a fraud as a fraud, because that would be bad for business. Where you see someone walk into your bank, or where you see someone walk into your customer and say that, because a model say this person is a fraud, whereas if the person is not a fraud, that would be so bad for business. So we'll be needing a model that is very, very accurately and it is very what precise. So that is used so that you can say that this is an example where we can use what the precision what accuracy. So in precision accuracy, in that place, we'll be needing a model that it is very, very good at evaluating for precision. That's evaluating for a false or positive. We don't want to classify something that is correct as incorrect. And then in the case of recall, so recall, it means how many of the actual classes, that's how many of the positive classes were not positive. So how many of this is the actual cases were able to predict correctly with our model. So we want to see how sensitive is our model. So let's say, for example, we have 12, or let me give a case study of where we have 200 data points. So out of the 200 data points, we are having 50% of it, or sorry, 50 out of 200 that occur is a fraud case. Why 150 is not a fraud case? Now, if we want to check, okay, how very, very sensitive is our model? And our model is classifying 48 out of 50 as a fraud. It means our model is 96% what correct, right? Because our model is able to classify 48 out of 50. So the sensitiveness of our model is what is 96%. Now, F1 score is like the mean of the harmonic mean rather of both your precision and your recall. So it combines both your precision and recall. And in most cases, most classification uses what the F1 score. So it is, I think, 2 times the precision times your recall over your precision plus your recall. So that's the mathematical formula. We can also check those ones online. Then we also have area under the receiving call. So this is a probability that plots the true positive against what the false positive. So it is taking the class that occur and the class that do not occur. Try to plot like a curve. That's a curve of occurrence and see, okay. And in AU and ROC, it means if you are getting an AUC of greater than 0.8, it means your model is doing very well. But if you are getting a model lesser than 0.8, it means your model is not doing well. And if you get a model of 0.5, it means your model is bad. So those are like the key point, or those are like points you should note in using AUC. If you have a score of 0.5, it means your model is very, very bad. It means you're having a score greater than 0.8. It means your model is doing well. So, but it does not mean it is perfectly, but greater than 0.8 means it's doing well. And you can also try and improve it. So towards the mark of 1. So the scale is from 0 to 1. Then we have also the log loss, which most times is called the cross entropy loss. So most times it's used in classification problem. And most times this log loss is used in a multi-label classification where you are asked to predict the probability. Now, there is one thing that I always let people know. In the case of classification, you can never get the probability in classification. So if you are doing you can never get the probability of regression. So those are two different things. In classification, you can get the probability of if something occurs. But while in the case of regression, you cannot get the probability. So that's another use case where you can use classification. You can try and find, okay, what is the probability of this particular value occurring? So you can also use classification. I think this should be the ending of my slide before I move into, okay. So before switching to my code editor, so if you have any question, please just do let me know. Let me quickly switch to launching my notebook. So sure. So please someone should indicate if you can see my screen. If you can see my screen, I have my notebook launched up. So I know that. Okay, visible. Yes. Okay. It's okay. Let's continue. So I'm trying to upload the data sets that we'll be using for today. So I'm not using my local machine. Yes, so what I'm using is Google Colab. Oh, this is Collaborate. Yeah, so didn't save the previous version. So what this does, yeah, so now, okay, we have everything correct. So this is, I'll be using Google Colab. So we'll be working through the solution. So now, let me quickly show what it's a sigmoid function. So we can see what is a sigmoid function. So you can see the sigmoid graph. So what it does is it uses the Euler number. So this X means what? The probability. So in the case of, because I said logistic regression that is a sigmoid function, and in the case of this, X means to be the output. So if it passes in through this value, it's append it from what? From 1 to what? 0. This is a simple graph of it. Let me check if I can get a graph for it. So you can see this is a simple graph. So anything that occurs within this, it appends to this. Anything that occurs after this, it appends to this. Now, so let's quickly move down to so any number that occur rather below 0.5 or below 0, it takes it to 0. Any number that occur below from 0 to a positive number, it takes it to 1. So now let me check the cat boost model and scikit-learn. Yeah, so this is scikit-learn. So we can just get an understanding. So this is, so you can see the first thing, it says that it's an open source gradient boosting library. So let me check the creator. Okay, so you can see it was released by what? Yandex. These are people that they work. Yandex and a Russian company. So they're the one that authored the paper on Scikit on CatBoost. There are also other ones. We have Light GBM, which was done by Microsoft. Then we have XGBoost, done by some researchers at the University of Washington. Yes, so we can see this is different classification algorithm. So machine learning in Python by scikit-learn. There are different algorithms that have been implemented. So we have regression. We also have clustering. So we have dimensional reduction. We have model selection, pre-processing. Name it, you would see most of them there. And you can go to the GitHub repo. So the GitHub repository, I think, yeah, so you see it. So the GitHub repository shows how you can contribute to it. So yes, so how you can contribute to it. So this shows the number of people that have contributed. So you can see contributors, 246. So if you have anything that you think you can contribute to it, you can also contribute to it. So these are the number of people that have used it. This is a simple overview of how open source works. So open source means you can go online and see the code and you can use them. So let's quickly rush into a linear model. So under linear model, we should see how logistic regression works. So logistic regression. So okay, so this is logistic regression. Yes, I guess this should be it. Okay, yeah, so this is logistic. So you can see the whole code base for it. So you can try and just download it and see if you want to make any changes to it. So this is the whole, this is an algorithm. This is over how many pages? Oh, sorry, how many lines of code rather? So because this is documented, so it is 236. So because it's documented, that's right. So there are different functions here. So let's quickly run into our code. So the first thing we do is we import our libraries. So we have pandas. Let me think if I can increase this so everyone can see. So yeah, we have pandas. Then we have NumPy. Then we have request. Sorry, this is for regular expression. We have matplotlib for plotting. Then we have Seaborn for also plotting. Then we have label encoder. We'll see how we can encode alphabetical numbers. So this is the first thing. So this data set was gotten from Zindi, an online platform where you can do machine learning competition or do machine learning problems. So what we'll do is we first read in our data set. So if you notice from here, I passed into data set, which is countries, continent, and train.csv. So you'll be seeing how to use them. So this is our train.csv. So I've passed in both of them and I try to read it. So it means I'm loading them. So you can see we have different examples. So this, we have different countries, then we have different age group. Then we have what is traveling with, either with a children or a spouse, the total female, total male, purpose. This is just an understanding of what's the data. But this is what we're predicting, the cost category. So we'll be seeing what the cost category entails. So let me quickly bring that. So we can say train, then the cost category. So I want to check what the value count. So value count will quickly estimate, what are the counts for each of the occurrence. So we can see, let me convert this to, let me say, divided by the ship. Then, okay, let's go start. Sorry. Yes. So we can see the percentage of how each of them occur. So a normal cost occurred 29.5%, higher cost 26, high cost 19, lower cost 13, low cost 8.4, then the highest cost 1.93. Yeah. So we can see it. Now we can see that we have 1, 2, 3, 4, 5, 6. We have 6 different labels. So this is a simple problem where we're working with a multi-class classification. Now, the next thing we'll do is let's try and find relationship in our data. The first thing is what exploratory data analysis, which is trying to check if our data has missing values. So in case of missing values, this is the function we use. Is NA checks if a particular column has missing value. If it has a return a Boolean value, either a true or a false. So what sum does, it estimates all the values for true. So it means we are having 1,075. So, but before then, let us check the shape of our data set. So our shape shows what is our rows and what is our column. So it means you have 18.5K rows and 21 columns. So from our columns, we know one of our columns, which is the cost category, is what we are predicting. Definitely, we are having 20 independent columns and 1 dependent columns. Now, the next thing is, what is the missing value? So we can see our missing value is 1,075. Then for total female, we have 2. Then for total male, we have 6. So the next thing is, this is just, we're trying to plot a heat map to see that, if there is a missing value. Now, if you notice, we are only having this yellow indicates there is a missing value. But because of the occurrence for total female and total male are very, very small, let's try and convert it to percentage so we can see. So train.shape index 0, let me quickly do this so we can see, takes out the first value. So that's what we're using. Then if I say 100%, so you see that it is very, very minute. So this is 0.001, which can also be approximated to 1 decimal place as 0 for total male and female, which is the number of missing values. That's why we are very sure we are not seeing them here. So that's why most time visualization does not bring out all the total number or all the occurrence. Visualization does not only show how there is to it. So we can try and do manual data analysis to get a better understanding before deep diving into visualization. So you can see this is a case where visualization did not show us all there is to our data set. Now, so this is, we're trying to plot, okay, what are the counts for our cost category? So we are using Seaborn. So we can see that the highest of them here was the normal cost. So let me try and increase the fee goal. Then fee size, I think something like this. 10 by 8. I think this should be larger. Oh, it's too large. Sorry. And do 6 by 10. Yeah. Oosh. So sorry, X and Y. So let me do 10 by 6. So I want it, okay, yeah. So you can see that this alone, it's very visible. So you can see that the highest is what normal cost has more than 5,000 occurrence. Then the lowest is highest cost. It has lesser than 1,000 occurrence. Then the next thing is we want to try and find, okay, let's try and check relationships among our data set. Then we pick in the main activity, which is this. A column of the main activities, we have different activities that occur. If it's a beach tourism, if it's a wildlife tourism, and different kind of activities that occur when you went on travel. So if you remember, like I said, our data set is a data set that shows if a person travels to Tanzania, what are the likely groups of costs in which they are to spend based on the amount they spend in Tanzania. So this is, it groups them into different costs based on what they ordered, based on the amount of time they stayed, based on amount of people that came in, and which kind of visa or which kind of mode of operation they entered into the country, and what country are they grouped into. Now, so we can see that for this one, we have the tour arrangement. So our tour arrangement is like, how will I put it, different classes that we're grouping them into. So either if it's a package tour and independent tour. So this is very easy. We know a package tour, it means it is someone that packaged the whole tour, or it is organized by a group of people, where an independent tour is done by, okay, let's say a single person. So that is what this one explains. So that is what this visualization does. So we're just doing a simple visualization to understand what our data. Now we try to bin so before the let's quickly check to see what is the relationship of our data. So if you check the relationship, you can see for our data, we have most of them are objects. So when you see object, it means they're categorical. So categorical means what? They are alphabetic. Then we only have some values which are float 64 and float total male and total female. Float means what? Decimal numbers. While integer means whole numbers. So it does not have what? A decimal. So they are different things entirely. So an integer can never have a decimal number, but a float can also act as an integer, but it always have a 0.0 at the back. Yeah. So those are the two differences. So we have four different numbers that occur out of 20 columns that we have. So it means we'll try and encode the other 16 columns. Now, this is just trying to do a bin relationship for the female and both the male. Then the next thing is, these are just exploratory data analysis, just to get an overview of our data. Now, the next thing is to try and find, also these are also visualization plots, just to get, okay, what our age group is, what are the classes, which of them occur the most in a particular age group, to know how they spend, right? So these are visualization. Now, since we know that our data has missing value, so and travel with mode, which was what we saw here, has the highest number of missing value. So we try to fill it with what? The mode value, which is what we did here. You came down here, we say, okay, let's get the mode. Mode means what? The highest number of occurrence. Then for the median, for total male, we want to fill it to the median. Then total female, also want to fill it to the median. Then you can see we have train, we index out the column. Then we said fill with any. So fill with any means what? We are using, we want to fill all the missing value with a particular value. So we fill the travel with what? Alone. And we also fill this with what? With the median, which is 1. Yeah, so now let's try and check the values. Now let's do something like this. Train dot is NA. So let's try and see if what we've done is correct. So we can see that, so we don't have any, all of them, all our missing value what has been filled. So now the next thing is let's encode the country column to continent. Now, if you notice, different countries belong to different continents, right? So that's what we'll be doing. So this is just a Python code that encodes all the countries that occur into their respective continent. So this code will be shared to you so you can run through it and see. So we have Africa, we have Asia, Europe, Oceanic, North America, then South America. So this is just a simple Python function. So when we run it, then we try and see, okay, we have Europe occurred the highest, then the least occurring was what? South America. So it means most South America do not visit Tanzania based on the data set we have. Then Europe are the ones that visit Tanzania the most based what? On the data set we have, closely followed by what? Africa. So we can say from this now, Africa is visitation is ×2 of that of Europe. So that's like an illustration, which is also very, very feasible from this. Then we can try and also plot, make a color to see that, okay, based on the country, the continent rather, in which they belong to, how do they spend or what is their cost category? So that's what this does. Now, so this is also a function that try and find the value count. So value count means for each of the columns, how many times did they occur, right? So we grouped our cost category, then we index out what the country continent. So each of the continent from the cost category, how many times does high cost occur in Europe? How many times does it occur in North America? So we get an idea like that. Then transpose, without putting transpose, let's see what comes out. So you see we have a very long data. So transpose, like convert it to, that's it, invert it from, so it changed, that's like converting from horizontal to vertical. So transpose. Yeah. So now let's try and do a feature interaction. So feature interaction tries to find the relationship between two. We are trying to find the relationship manually by ourselves between two different values. Now, the first thing is we can say, okay, if your age group and who you travel with, you can measure together to form a particular relationship. Your age group and what is your purpose to try and form a relationship. How your tour was arranged and your age, we try and form. How we did this was because if we check our age group and our travel route, those columns are categorical. So that's why we can use this method. But if it is a numerical, it means you're adding them. There's no need for fixing this space. Yeah, right? Because these are string values, which are object values. That's why we're fixing this space. So we can concatenate. So the process of adding two different values. So from our simple Python, let's say x is equals to Emmanuel, then y is equals to, so this is just my name. So if we want, I can say x plus space y, that's to form my full name, right? So I can say let it be equals to my full name, which is this. So if I call my full name, I should be having, yeah, Emmanuel and space bar. But if there's no space, look at what comes out. You can see there's no space. So that's the reason for doing this, right? That's the reason for doing this. Now, so this is what feature interaction. We try to find the relationship among our data set. Now, the next thing is, this is a case where we want to find, okay, if a particular person spend particular night in mainland, then you also spend on Zanzibar. Now we can try to find, okay, what is the total nights the person spend? It is very logical. What is total nights the person spend in Tanzania? So we add both of them together and find, oh, this is the total night. Then the next thing is we try to find what is your age group. So if you are greater than 65, it means you are in a category 4. If you are greater than 45, you are in another category. If you are greater than 25, another category, like that. So these are just simple analysis. So we call most time they call it feature interaction and feature engineering. So you are trying to generate new features from our initial data set. Now, so what this does, if we notice from our train, oh, I already encoded it. So let me quickly revert to not encoding. Okay, coming. Okay. I encoded the values. So I want to explain what encoding does. So in the case of encoding, it means we are converting a categorical value to numerical value, right? Now, we had 16 different values. So we had 16 different values that need to be encoded. So we'll be seeing how they were encoded. Now, let's take, this is our train.head. Now, let's see, we have Italy as a country. We cannot pass in Italy into our model because it does not understand what Italy means. It means we have to encode it into what? A number. So this is what this function does here. This is list comprehension. It removes a cost category. So let me isolate this and run this on its own. So let's see. So if I run features, it gives me what all the available features, right? So I want to convert it to an array. Very easy. So it shows that it brings out all my columns from here, as you can see. So it brings out all the columns. So you can see them, the column names. It brings all of them out. Then it removes the cost categories because that's our dependent variable. We don't want to encode it for now. We remove it. Now, what this one does is it tries to find np.dtypes, try to find, okay, what are the categorical features? So if I do cat underscore fit, it brings out all what the categorical feature, their array, right? Their array. Let me do something like this. Okay, let me do for I in cat.features. So let's say let's do features or train.columns dot to underscore list index. I think it has something like this. Index I. So let's print this out. So if I'm printing this, okay, cards fits, not features. Yeah, so you can see we will not find anything like we shouldn't find anything like the total females and total males because those ones was their categorical value. So we did not find any, right? So those are the two categorical values that we know, right? Now let's quickly switch to this so we can continue. So what this one does, we use what? Label encoder. So label encoder. So you can see the scikit-learn library. So it encodes all your value. That's it takes your category. So you say for encoding categorical feature as a one encoding numerical array. So it takes, let's say, for example, you have 3 classes. It converts all your class from numbers, from alphabet to numbers. So it gives them a relationship of from 0, 1 to 3. So let's say we have 7 classes. It gives them a class from 0 to 6, right? So all the classes that occur, let's say for Italy can have, for this country now, Italy can have a value of 1. United States can have a value of 2. So anywhere you see in the United States, it converts it to 2 so that your model can understand, okay, this is your relationship, right? So that's what label encoding does. It encodes all your data into numerical values. Now, so if we try and check the head of our column, we can see we have all numerical, right? All of them are numerical. All of them are what? Are numerical. So now let's come here now. We want to encode our target. So if you notice, our target is what? The cost category. Then we say high cost equals to this. like that. So this like a simple function that shows. So let's pass it into it so we can get ours. So we can see from here we have our X value and our Y value, right? So our X should be all our attribute that we'll be using, while our Y should be what? Our target. So you can see now. So from here, we can see that our normal cost is encoded as 2, which was what was done here. Normal cost is equal to 2. Then 4, which is the higher cost, was 4845. So we can see it here, 4845. So we can see that what we the function we wrote here was very, very very, very correct. Now it's time to build our classification model. We'll first be using a logistic regression. So the first thing we'll do is run a train test split. So this is from scikit-learn also model selection. So like I said, we group it into a train, a test, then a train for target, a test for target. Then let's say we're using 25% of our test data. So 25% means we're using from our actual training, we're splitting our data into 25%. Now there's a simple function I want us to add. So let's put in stratify. Stratify, it's equals to what? Y. So what stratify does is that in both our test and our train, so let me bring this down. Let's Y underscore train. Let me do value count. So you would see, let me find Y underscore train. Let me do the length. So I want us to quickly see what stratify does. Yeah, so this should be test. So you can see most of the relationship are what? They are almost the same thing. So 2 are 29%, 29% like that. So you try to split it so that we don't have like an imbalanced data set. Now let's remove stratify and see how it will occur. So now you can see from here, we had 2 was around 29.4, while this one was 29.9. This one was 26, this was 25. Here was 19, here was 20. Here was 8, while here was, 8.6, 1.8. So stratify try to create like a balance between all our data, right? So if you are in classification problem, always try and use stratify. So that stratify would try to create a simple balance among all your data. So now the next thing for us to do is fit in our logistic regression model. So we call in our logistic regression model, then we fit it into it. Now, like I said, in the area of machine in classification, we can find what's the prediction. So what this is our probability, predict what probability. So we can either predict the hard class or we do the probability to find what the class. So let's run it. So now, since we're getting our target variable, since the multi-class is in 6 different shape, right? So we'll be having 6 different what probability. So let's check the prediction probability. So the prediction probability shows what are the possible number of occurrence. Let's index out the first one. So we can see it. So if we try and do what is the sum of this? So mp.sum, it should obviously give us close to 1. Yeah, 0.99. So what this does is that it aggregate all the value for you. So this is the occurrence for a particular one. Then, so you can see that the most occurring is this, which is having 6.0 raised per 3, 6.03, which is E minus 1, which is 0.6. So what our model should be predicting should be predicting a class of 3, right? So let's try and check what is the predictions for index 0. We should be having a class of 2 rather, not 3. So because this is 1, 2, 3. So this is index 0, index 1, index 2. So that's why we are having a 2. So we can see, let's check the value of 1 and see if on the right track. So we can see the highest value here was what 0.4. among all of them. So definitely our prediction should be 0, right? So that is how it works. So you can see, you can now try and define the threshold for it if you want. So the next thing is, let's evaluate our classification metrics and see. So this is the case. So scikit-learn already has everything coded for us. All our evaluation metric, from the F1 score to the accuracy, to the balanced accuracy, to precision, ROC, and everything. So what it does need to do is call the library.metrics, then import whichever of the libraries you want. So we can see from our accuracy score, what our model is predicting, we're having a class of 52 or 52%. Then we are having an F1 score. So you can define how you want your F1 score to be, either it is known or should be weighted. Now, these are different values, but let's take note of how the F1 score is. So our F1 score here is 0.47. Then the balance accuracy is 0.374. So all these have different mathematical equations on how it is being derived. They are all gotten from the confusion matrix. How you have the true positive, the true negative, the false positive, and the false negative. Then the next thing is, we are running into the classification report to see, what is the classification report? So now the classification report shows each of the value. For the value of 0, what is the precision, and what is the recall, then what is the F1 score, right? Then because we have 6 different classes, which are coded from 0 to 5. Now it shows each of them. So we can see now, for our case of 1, we are having a precision of 0. Let's say, for example, in our case, we want to build a system that has a very precise value, and we are having an accuracy of 0.0. It means our model is performing worse in predicting this case of 1, and it cannot be used. It has to go and be optimized. So the classification report will show the individual metric for each of the classes. So you can now see and estimate that, okay, how best is this class being predicted, and how best is this class being understood by my model. Then we have a log loss. So all these are already done by my scikit-learn for you. So log loss, like I said, uses your prediction, the probability. So let's check how log loss work. So these are those. So this is how log loss work. So okay, these are just the codes for it. So I think you spare time, you can try and just go through them. So please, if you have any question, also drop it on the chat, right? Also drop it on the chat so I can follow through. Then the next thing is to pass in. We want to try and say, okay, we've done for logistic regression. Let's try and do for so this tree modeling. We can try and say, okay, we've done for logistic regression also, which is a linear model. Let's try and work on a tree model and see, okay, if it performs well. So like yesterday, we trained a random forest and regression, a decision tree. Now we'll be training an exampling and a gradient boosting classifier and a decision tree. So we import our value from scikit-learn, which is sklearn, then random forest, we initialize it. Then the next thing is to fit into our train and test, in which we've already done, right? I think I have a question. Okay. So the next thing is we're fitting it into the model. So this is a training process. You can see it is loading. It means it's training. Then, so it has finished executing. So the next thing is let's try and train. Let's do a prediction, and let's do a prediction. Then we'll also be doing the probability also for it. So let's run it. So very easy. Let's try and run to see, okay, for decision tree. Now let's come back to see our logistic regression. If we notice some logistic regression, let's take, for example, we're analyzing the accuracy score. Our accuracy score here was 0.52. But for decision tree, we're having 0.46. We see that, it is doing bad. But if we check our precision for value of 1, we can see that we are having a value of 0.00 using logistic regression. It means our logistic regression does not understand this class 1. But our decision tree here could be able to grasp a little bit about it, having a precision of 0.22. So if you are focused on your precision for the class 1, it means you will be able to rely better on your decision tree than on your logistic regression. So this is an application of where you are the one defining what your result or your evaluation metrics. Now, if we see for our random forest classifier, it has an accuracy score of 0.56, which is better than logistic regression and decision tree. Also, we see the value of 1. The precision is 0.27, which is also better than both the decision tree and our logistic regression. Now, let's just move into the gradient boosting machine. Then we see that, oh, our gradient boosting machine even performed better than both of them combined. So we can say that, okay, our gradient boosting machine is actually a good classifier. Then the next thing we can do now is we can try to find the hyperparameter for each of those algorithms. So in hyperparameter, you're trying to find the best parameter that best suits what our model, or that best suits our data rather. So that is what we do in this case. So trying to find our hyperparameter. Okay, so this is what I did. This is for a grid search. Ooh. So I'm trying to perform an hyperparameter for a grid search. I guess this will take a lot of time. I shouldn't have run this. So what this does, so a grid search means it is trying to find the relationship among all the data points specified, different parameters. So we specify the mass picture, different, then the depth, then the criterion, and try to find, okay, try and find an optimized parameter for this, for all this. So that is what a grid search does. So what the grid search does is to find the relationship, then map it to our data to produce a better and an improved result. So that's what a grid search does. I guess it is currently running. So please, if you have questions, drop it on the chat. Okay, yes, you can, for Mr. Oladipo, you can use it a lot for research purpose. I think I've been able to contribute to some research paper using machine learning, even though we've not published it yet, but yes, you can use it. Classification analysis a lot. I think I used it for one. It was CatBoost I used. Yeah, so that's why I said you have to understand how they work, the algorithm, how they work. So before you can just say, oh, you've trained something. Yeah. So my model is currently training. This will take a lot of time, a ample time. So now let's just quickly review the basics. So let's quickly review the basics. Why this is training. So please, if there's any question before we end this section for today, I think we've used more than the time. So I'm so sorry. So please, if there is anything that is not clear to you, just let me know so I can explain it while our model is currently training. Yeah. So please, if there's any question, please just let me know. Let me know. Let me know. Yeah, so let me quickly show this. Now we can see that the accuracy for our gradient boosting tree was 0.82. But the model here, our training is also what you can see we fit in, we randomize grid search, try to find a random parameter, while grid search try to do a total grid search. So you try to use all the methods, while randomize does pick each of them randomly, each of the parameters, and try to feed them in. Now, the accuracy score we're getting from here was 0.5826. Why? You can see we're already having a score from here of 0.587, right? Based on this parameter, the criterion should be the squared error, the depth should be 3, and the mass depth should be, mass feature rather, should be square root, right? So we can see this is a way in which we can see that, oh, grid search can give us a better result. But in using grid search, most of the time, performing like a good or an optimal grid search produce a good result, but it does not per se increase it like to a very, very good extent. But it does give you like a push of your model or a push of your data to get like a better accuracy. Yes, it can be implemented in power plant performance. I think it is used in predictive maintenance, also predictive maintenance. It is used, I think it is used in the field of mechanical engineering. Yeah, you can. If you have the data, yes, you can. I think there was one, just sorry for diverting there, I think there was one problem in which we worked on, that was using audio data set. So it was trying to find the noise in a power plant. So if the noise can be the noise from the manufacturing, that's from the manufacturing plant, or it's a noise based like on a faulty machine. So that's the case of using anomaly detection, or using the noise from a manufacturing plant. Yes. So that's a different area. That's we use artificial neural network. Yes, that's deep learning. Yes, we use deep learning. Like Peter said, we would also get to that one also. So it's just like a gradual step. Oh, so how can someone be so good in this? So being good in something is constant practice, and daily research. Yes, daily research. You try and read up on what people has done. Try and implement what has been done. Like I said in one of them, I said you can check a research paper and try and read it and try and re-implement it. Why this is currently training, let me check if I can get a paper on, okay, cat boost paper. I think it is, yes, unbiased boosting machine. So this is the paper that was written. So you can try and implement everything on your own again. Okay, yeah, we'll drop everything on the group chat. So this is a PDF that shows how to use CatBoost. So CatBoost itself is a gradient boosting machine, but was developed by Yandex, and they released the paper. So this whole paper was on CatBoost and the whole learning algorithm. So you can understand, okay, how does it work? So you're not just like because you're just using a library, you don't know how it works. You can try and read on how it works to see that, okay, if there are things I can change. So CatBoost initially, as the name implies, it's called CAT. CAT represents categorical, while boosting means a boosting machine, right? You can use CatBoost is very, very good for encoding categorical feature. So that is why most use cases. So if you have a data set that has a lot of categorical feature, CatBoost is your best source for you. So you can use it. So this is just a paper on how the method works. And you would see different experiment that was performed. So you can see here, like GBM. Let me increase this. Yeah. So you can see this is a data set on how they were performed on. This is CatBoost benchmark data set, like GBM, SGBoost. These are the three best gradient boosting machines currently being used in the industry. Yeah, currently being used in the industry. So you can try and research on them and see that, oh, what are the kind of data set that I can, or the different algorithms that I can use in training out my model. So we are not just limited to only logistic regression and the likes. We can also use other. You can use other ones. We also have, I think, histogram, or yeah, history gradient boosting machine also. I can't really recall it, but you can make research on them and try and find different gradient boosting machines and try and read on them on what they work. So what we just thought is the implementation. I think this will take forever. I don't know. So please, if there's any question, just try and drop it on the group chat. In the next 5 minutes, I think I should be rounding up the section. Oh, someone is just joining now. Wow. So I should be rounding off for this section. Yeah, please, if you have any question, can just drop it on the group chat so we can know. How can you have the PDF? Yes, we would share everything. We would share everything on the group. We would share everything. So we would have, like, I think, a drive where we can share to everyone, both all what was used throughout the whole training process of this program. We would share everything. So in the next 4 minutes, I should. Okay, yeah. So you can also follow us or check us on Instagram, on all our social media page. You can follow us. Yeah. So for those that are having issue that did not follow, most of our Medium articles would also be shared on the group, but would also reshare them again. They contain all what has been taught and beyond that also. So they are very, very good articles that you can read up. They are very, let me think if I can get one. So you would see Medium. Yeah. So you see them. They are very, very good articles. So you can see what has been taught: matrices, vector, linear algebra, visualization on Python, why pandas really, but why pandas really, particle data science. Let me just open one so you can read them and see, oh, these are good content. So for to also what aid your learning also, right? So you can see this, I think this was taught, this is a case of using artificial neural network. Yeah, but what it does boils down to is the mathematics of machine learning, where we talked about vectors, we talked about matrices, we also talked about tabular data sets, role encoding, basics of linear algebra, and software for linear algebra. So we use NumPy. We talked about NumPy also. We also use indexing for NumPy, basic operation on an array. I think we also talked about a sparse matrix. Yeah, yeah. So you can see, you can try and read them up if you have any issues. Very easy. You can just try and follow us. We would also share them. I think, let me check for our YouTube page. Ooh. Ooh. I think it's my YouTube I should call it. Don't know. So let's just check and let's see. So, oh, in the next 2 minutes, I should be ending the section. We've spent enough time. Thanks to everyone that joined. Thanks to everyone that joined in. For the case of hyperparameter tuning, I will share the results. Oh, I think we already got a good result also. So we already have a result here of a score of 5.88. So which was better than the initial one of 5.87. That's a decimal point of 0.01, which is also a good result if you are conducting research. That's based on what you want. So this is what Grid Search does. It gives you a very, very good parameter to increase your result of a bit. Oh, well, thank you very much. I am highly welcome. So we'll be ending the section in the next 40 minutes. So thanks to everyone that joined. I think we should be having a section on Friday also. So we'll be able to round up. Okay, so let's just check this is yeah, so this is our, let's try and check us out on Google and see. So you can see this is our own website, this is our Facebook and Twitter rather. So you can also try and check us out. So I should be ending the section very soon. So all the contents that are being used also will be shared also here. So you can try and check us out and see what to do, why choose us, why you want to learn with us, why you want to grow with us, this kind of service we offer. So we offer different services also. So what do you want to do? So these are like our first events that we're organizing, so you can see them. You can engage with us on a different platform. Yeah. So you can follow us on all our social media platforms. Yeah. So I think we already have the final results. So you can see we have a score of 0.580, and these are our final results. So I think that's all for today. So in 2-3 minutes or 1 minute or so, I'll be ending the section. Thank everyone for joining us today, and we really appreciate you. So you can follow us, yes. Yeah, this is us, and you can follow us on our social media platform. Right? You can follow us, and this is for us on Twitter. So we post AI content. So all our posts, you can see them. We post was an API. We talked about them. We post most of our content, right? So you can obviously see them. So thanks once again. So you can see statistics, what we've talked about, we already posted on our content some days back. So thanks once again for joining us in this section. And we hope to see you in our next class or our next bootcamp section, which will be like a roundup of everything. So thank you all for joining, and we wish you all a good rest. Thank you.